All right, so this is now trying to apply this simplification theorem. The idea is to detect quickly either a Tevna or Norton model and apply the equivalence between these two models to simplify the circuits. So this is kind of more like a drawing computation or a drawing way of solving the problem. So let's see. Here is my circuit. Can I see any Tevna or Norton model? The answer is yes. Remember that I don't want to apply any model, including this R, because if you now simplify the circuits including this R, you will lose the information, the unknown you're looking at, which is the current. Okay, so do we have any Tevna or Norton model on this circuit? The answer is yes. You have here a Tevna model and you have here a Norton model. So let's redraw the circuits applying the equivalence between these two models, and I'm starting from here, number one. So this is just, as I say, a redrawing things. Let me just, can I grab this and make this here? So let's redraw just the circuits. And I'm applying here the equivalence on number one. And if I do so, I'm obtaining this. So nothing more than switching from Norton to Tevna, as I showed you last time. So something you have to keep in mind, I keep the direction of the parameters here. The current is going down, and I keep here in my Tevna model the voltage going down. The resistor is R1, and I keep it R1 here. And to get here the value of a voltage, I multiply R1 with I0. Fine for everyone here? Then I'm moving to the second part, which is considering this part here. Still redrawing. So this time I move from Tevna to Norton. So this. So the value here of the current flowing in this direction is E over 2R1, and the value of the resistor here is 2R1. Again, here you have here you have a voltage generator in series with this resistor. When you move back to this, well, you're switching to Norton model, you keep the same resistor. These two resistors are the same. And then here, the current generator, again, you do have the same direction here going up, and the value of the current delivered by your generator is this voltage over this resistor. Is it okay for this simplification that we are using each time, how we can move from one model to another? This is really important. Yeah.
Actually, I'm not sure I understand why are we switching from Tevnan to Norton? Why do we have to change like that?
the idea, you will see that little by little, we're gonna simplify the very first circuit, these kind of complex circuits. Little by little, we will try to simplify it back to a single mesh, sorry. So let me keep going through the simplification. And right now, I haven't done any computations, anything to get the current. I'm just redrawing the circuits to try to simplify it little by little. Let's keep going, and it will answer your questions. So now I have this, okay? Do you see any kind of extra simplification or association we can make? The answer, of course, is yes. We can take care of these two resistors that are in parallel. That's gonna make a single resistor, which is R1, okay? So, it's a bit large. So now you face this, and can you do something else? Do you see any Tevna or Norton model? Well, here you still have your Tevna model that you can move to a Norton model, but it's not helping you really. So the other thing you see is now that you have a Norton model here that you can switch to a Tevna model. So again, redrawing. So this time you have this with E over 2 R1. Then you have the famous R, which is this R1 here. You have this and this. So you end up with this circuit, still looking at the current here. This is the initial current flowing through the R that I didn't change at all. So now, sorry, you are in front of a single mesh circuit looking at the current flowing in these circuits, and this is going to be super simple to solve. You can actually, you're looking at a current in a single mesh circuit. You can simplify everything again, because this won't change the current flowing in this single mesh. So you can actually, if you want, redraw here. You have two, oh, I'm sorry. So all the resistors are in series, so you can have a main resistor which is 2R1 plus R. Still looking at the current flowing here.
Isn't it just R1 plus R?
No, because you have one R1 here and another one here.
Okay, sorry.
And the value of the equivalent generator is E over 2 plus R1 I0. And that's it. So now you can check for the voltage here through this resistor using the receptor convention. Let's call it U. You apply the mesh law and you can deduce that the current I equals to E over 2 plus R1 R0 over 2 R1 plus R. Is it the right result? I hope so. Yes, it is. No? There is a sign problem? No, there is not. So this is the way of using simplification and equivalence model. Try to simplify as much as possible your circuits to at the very end get only a single and quick equation to do to gain the result. Is it clear for everyone?
Yes.
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 Okay. Yeah.
And so is it most of the time that we use the simplification with this?
Yeah, sure. If you give you the choice, as you can see, this is super fast to apply and quite easy to handle, and you can simplify, really simplify very quickly a circuit. So yes, if you have the right to use it, if we allow you to use whatever method you want, yes, if you see that this could be a good way to go, please go for it, yes. All right. Any question? Is it clear? Moving quickly to one model to another one, just want to remind you that you have to keep the direction of the parameters that you consider. So when I was moving from this Norton model to this Tevna model, I keep here the direction, so the current was going down here, still going down. When I move to this model to this model here, actually this was going up. So here, from here to here, still keeping the direction upwards. That's it. That's the main mistakes you can do. Can we move to the next and final theorem, or do you have questions?
It's fine for me.
Apparently no.
It's also fine for me.
Okay. So, next page. Now, final theorem, then maybe the more complex to understand. The so-called Millman, I don't remember, is there one N? Yeah. Millman theorem. So, Millman theorems is just another way to write the node law. Actually, what we are going to do right now is move to the I'm going to take maybe 1 minute to grab the past exam from last year, which was a demonstration and the introduction of Millman theorem. And this is going to be a good practice for you to work on that. So just give me 1 minute and I'm going to give you this to work on. And I don't see And this the case. Yeah. Perfect. Should have it in English too. Here we go. So, bureau. I have 3 different screens, so it's a bit hard to see it. This was the exam from last year. And we move to this exercise. So the idea behind this exercise was to just try to understand Millman, to discover the Millman theorem. So please go for it. Try to make this exercise, which is, I think, quite well described. But if you do have questions, please let me know. So the idea first is to demonstrate and understand Millman's theorem. First, we say identify the points that have the same potential on these circuits and apply the node law in A to get the link between the currents and the different the different currents. So you have, yeah, it's working perfect. So you have one current here. So yeah, first current here, current. Then you have a current flowing in every branch. One, two, three, four. And the idea is, okay, where do you see that some points have the same potential? In fact, every point here, and now you get used to do this, all of these points here have the same potential, right? They are linked together only by wires. So actually you can do something which is here, one branch, another branch here, another branch there, and another branch here with another resistor, and here with your generator, starting from the same points, correct? Same for all the points down. Okay, these points here do have the same potential. They're linked together. I only put wires between them, so you can, I'm sorry, it's not really correct, but if you finish the different line, then you have all of them meeting at the same point. Okay? So the first question is quite simple. This is the node law. Now that you have this, and you consider that you have a unique point here called A, please apply the node law here in A.
I know it's not important, but why is it V for the potential between A and B?
Again,
With the mass.
yeah, remember that.
We usually write them U when it's a potential.
Exactly. I think I explained you this at the very beginning of the class. This is some shortcut that we used to write sometime, or electrician used to write to use V when we discuss potential. Remember that voltage U is a variation of potential, correct?
Yes.
But here, that since you have the mass here, which means that B VB equals to 0. So in fact,
Oh, that means that U is equal to VA.
exactly.
Okay.
That's
you.
why we call it V prime, but again, you're right, this is definitely a voltage.
Thank you.
So first point, quite easy to go. So here, big I equals to the sum of all the E from 1 to 4. Okay. You have all the currents entering, and only this current here is going out. Okay, easy. Second question, give the expression of every current as a function of the voltage R and V prime. Since we said that all the point here have the same potential, the point there have the same potential, then this famous V prime here between this point here and this point there is the same than this point here and this point there, same here, 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 and there, which is that you can put this every time. Okay? So this is quite easy now to get the current. Let me just write it for the first part here. You see directly that V prime equals to minus E1. Of course, as usual, you can redraw here the voltage in between the terminal of these two R resistor in the receptor convention, because I1, you see that I1 is going up. I'm labeling this downwards because of the receptor convention, and then I consider this V prime being equals to this minus 2R time I1. So you can deduce that I1 equals to so V prime plus E1 over minus 2R1. And you can do this for every branches. I will let you go through this very quickly. So once you have all the current, then you use the answer of question 1. So here you will have I1, I2, I3, blah, 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 with every time one expression depending on V prime, E, and R. Sorry, it's not R1. I don't know why I put R1. And you know that the sum of all these currents equals to big I. So I equals to V prime plus E1 over minus 2R plus blah, 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 blah. And from this equation, you can deduce the value of V prime as a function of everything. And so you get the answer of question 3. So you should be able to find that V prime equals to minus 2R 3 times I minus E1 over 3 plus E2 over 6 plus E3 over 3 minus E4 over 4. If you already have the result, don't try to find the numerical value of V prime. This is a bit useless. Go to the next question and try to apply the simplification equivalence method to get the Norton model of everything. So try to reduce the full circuits back to a single Norton model.
So I have a question.
Yeah.
I don't understand why at the end of the expression it's E4 over 4.
E4 over 6, my bad.
Okay, thank you.
You're all into the computations, or some of you are blocked? One.
It's fine for me.
Perfect. So then you can move to question 5, which is simplifying all this circuit to a single Norton model. So at the end, you have something which is this. So this is Q3, this is Q5. So this is IN, this is RN. So Rn is 2/3 of R, and In equals to minus I1 over 2R plus E2 over plus E3 over 2R minus E4 minus I. Is it good for everyone for question 3?
Yes.
Okay, perfect. So let me erase big this up. And just remind you something when you are simplifying a circuit is when you have multiple voltage generator in series, you can make a single brand from it, having this value, okay? And when you have this time current generator in parallel, which is going to be the case here, you can add them also. So only voltage generator in series that you can associate, and you can associate only current generator which are in parallel. Man, I can...
Excuse me.
Yeah.
I'm sorry, I'm still on question 3, but I can't find the same result as you gave.
So is it kind of a sign problem, or
I
so
don't
you
know
have
what.
almost it, or nothing?
Not,
Not really.
not really. I have an expression, but it doesn't really look like this one.
Okay. Another point that you have to pay attention at the very end, and this moved us back to a very first session, is that the look at the homogeneity, the dimension of your results. Just back here on the voltage, you're looking for voltage, okay? So check that in your expression, every component is homogeneous to a voltage. So here I have a resistor time a current. So by Ohm's law, we know that this is homogeneous to a voltage, so this is fine. So maybe in your expression, first thing to check is it homogeneous or not? If there is a dimension problem, then this is a computation problem. If this is not a dimension problem, then it's a sign problem. It's coming from some issue, maybe in something you missed in the circuit. You made some very tiny mistakes of signs, considering maybe one voltage in the wrong direction. All right. So why now? Still get used to this. I think that, yeah. So question 5, you end up with this equivalent Norton model, still with, let me change color here, V prime here. Yellow is not a good one. So you can deduce that V prime equals to 2 R1 time I. So question 3, no more problems. Everyone is capable of finding this final result. Question 5, it's applying the simplification theorem. So you do little by little. So you take here the first branch, apply Norton model, and you end up with something which is this U1 over 2R and 2R. You do this for every branches, then you have to add, because they are going to be in parallel, every generator. There are current generator in parallel, so you can sum them, and this is going to be the final value of the current IN. Then you will have all the resistors in parallel, and because of the value, this is going to be easy for you to obtain, and you will find the 2 over 3 R value, and you can deduce V prime. Then we are moved. Yeah.
I have a question because I find the same IN but with the opposite sign, and I don't know if here the sign matters.
It's definitely matters depending on the direction of IN. For me, IN goes up, but maybe you pick the other direction.
Yes, I did.
So that's fine.
I can. Okay, thank you.
So you end up with this result, but still we are not using Millman theorem. Right now, it's just a demonstration on how we can find V prime in different way. For the first question and the Q3 questions, actually here, the value you find in Q3, question 3, equals to the value you find in Q5. Okay, so it's different way of finding what we are looking for in this exercise, which is in fact the value of V prime here. When you apply Millman theorem, it's to get the value of a potential at a certain point. So please read the explanation of Millman theorem here. So yeah, first sentence, it said that, well, G is called a conductance, and by definition, a conductance, a conductance G is the inverse of a resistance. So you can get the value of a potential directly by applying Millman's law, which is the value at a certain points equals to plus or minus currents arriving at this point, plus the sum of the different voltages time conductance over the sum of the conductance. Seen like this, it looks complex and difficult, but it's not. So just to simplify, Millman's theorem is considering a node. Let's call it A. Then you have I1 here. You have a resistor here called R1. You have another resistor here called R2. You have a resistor here called R3. And here you have various potential. So in this example, if I apply Millman theorem in A, what it gives me? The potential in A equals to, do you have current entering? If it contributes to the node, which is the case here, I1 is entering, I put a plus I1. Plus here, the potential here is minus E3. The potential there is E1. The potential, sorry, E2. And the potential there is E1. So from this branch, I get minus E3 time R3. From this branch, I get E2 time R. Sorry, it's G. Because, sorry. So first here, it's E3 over R3. From this, it's minus, it's E2 over R2, and from this branch is E1 over R1, everything over the sum of all the resistors I consider. So it's 1 over R1 plus 1 over R2 plus 1 over R3. So you get strictly using Millman theorem the potential at a certain point. And that's it. So you have to consider, as you can see, and this is said here, it's a simple rewriting of the node law. Why? Because here you have a potential. Here you have current. So potential, it's called time I. So that's why here at the denominator, you have an inverse of a resistor. So the inverse of, let me rewrite, maybe this is more easy to understand, but if I rewrite the last VA expression, it's like VA 1 over sum of R time blah, 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 blah. So everything which is here is homogeneous to a current. And this expression 1 over R, in fact, is R. So this is kind of the Ohm law. R time a current gives you a potential or difference of potential. A potential, the units of a potential is volts also, like a voltage. So you're done, and the result is homogeneous. Okay, is it clear the Millman theorem, or do you want me to re-explain or give more details? So you need, when you apply Millman theorem, to consider every first branches arriving at a node. So you consider the node A. What are all the branches arriving at A? And then considering here the point. Something which is quite important, back to my example. If I just put this here, and let's say that you have an even more complex with something like this. with some other circuits here, remember that you have to stop at the very first potential. Here you know that the potential at this point has some values, then you need to consider only one resistor, or maybe there is nothing. If there is nothing, the question is different, but if there is other resistor here, you have to consider them. And when you apply Millman theorem, you only consider the first node. You don't consider the rest of your circuit because this is not contributing to the node A here. Okay, you consider only the direct branches arriving at A. If it's clear, then try to apply Millman theorem in the example here at the node A. So we kind of erase everything. The point A is here, same then here, and then here, same point here. So applying Millman in A means that you have to consider everything coming from these branches. So you have each time a certain resistor, and here I put different points E1, E2, 1, 2, 3, 4, to get exactly, to help you actually finding the value here at the potential at this point, which is quite simple because VB here equals to 0. This point, this point, this point, this point, 0. But here you have a certain potential at point A, considering this voltage generator. Same from here, this one and this one too. Okay, so try to write VA. You see that this guy here is going out from the node A, so we're going to start by a minus I. Then contribution of E at the point 1, you have minus E1, point 2 E2, point 3 E3, point 4 minus E4, and then you apply Millman theorem, which is first it's minus E1 over 2R, second one plus E2 over 4R plus E3 over 2R minus E4 over 4R over the sum. So 1 over 2R plus 1 over 4R plus 1 over 2R plus 1 over 4R. And you're done. Why? Because VA is V prime. And again, this time, this result from Millman theorem is the same than the result you find in the question 3, and the same result again that you find in question 5. So I give you the last minute of this session to try to finish the computation, try to understand this application of Millman theorem. If you have questions, that's the right time to ask them. So at this point here, you realize that Millman's theorem is super fast to apply, and you get the result straightforward. So you realize that this IN here is in fact this current there. And if you go quickly through the simplification of this, you put everything over 4R, then you get 2 here plus 1 there plus 2 here plus 1 there, which makes 6 over 4R, which makes 3 over 2R, which is exactly the inverse of the resistor that you have here. Physics is magic. You find everything equals to the same result. So you have demonstrated the same result multiple times using multiple various methods. But they are all originate from the same Kirchhoff laws, in fact. But as you see, it's more easy to use, and actually even in an exam now, you can use them directly without demonstrating it again. If this is fine for you, then you move back to the exercise we were doing and try to apply Millman's theorem in the exercise we were working on. Do you have question on this past exam and the demonstration and explanation of Millman's theorem? I'm losing everyone.
Not really, but I don't understand how we can apply it to the
Yeah,
before.
That's a good question, because as I say, Millman is only giving you directly the value of a potential at a point, right? So here, in the case of the exercise from the today, you have to apply it twice. You have to apply it at point A and apply it again at point B. So then you have VA and VB coming from Millman's theorem. So you apply it twice. And then you write VB minus VA equals to a certain potential, which is the voltage in between the terminal of R, equals to R time I, the current. So you get the current. I don't know if it's clear. I'm gonna just write it again on the board.
I understand the concept, but for example, the right part with R1 and